Okay, so welcome back. So at the moment we're looking at the quasi-permissionless and dynamically available settings, and we're considering various different ways we can separate these settings. Right. So in the last video we were talking about accountability. In this video I want to take a look at optimistic responsiveness. Okay, so remember, if you're working in partial synchrony, then we have this known bound delta on message delays after GST. Okay, actually message delays might be much less than that. Okay, so now we want to let lowercase delta, little delta, be actual and unknown bound on message delays and the message delivery after GST. Okay, I won't write down a formal definition of responsiveness and optimistic responsiveness, but hopefully I'll give a rough definition which will be enough to understand what's going on. So roughly, a protocol is responsive if after GST transactions are always confirmed in time order little delta. Okay. The latency, if you like, is a function of the actual message delay rather than the known upper bound. And often this could be quite important, right? Because your known bound delta might be set quite conservatively so as to ensure liveness. Right? You might have set delta to be 1 or 2 seconds, and then if the actual message delay is like a third of a second or something like that, then your responsive protocol is going to have much lower latency. Okay, so that's what it means roughly anyway to be responsive. And then we say a protocol is optimistically responsive if after GST transactions are always confirmed in time order delta, as long as all players behave honestly. Right? Basically what you want is in any period of time after GST, when people behave honestly, then the protocol behaves in a responsive fashion. Then your latency is a function of the actual message delay rather than your known bound delta. Okay, so first of all, let's see our negative result for the dynamically available setting. Okay, so here's the theorem. So there is no zero resilient blockchain protocol that is optimistically responsive in the dynamically available authenticated and synchronous setting. Okay, so basically it's saying the dynamically available protocols can't be optimistically responsive. So certainly can't be responsive. Okay, so this is fairly easy to sort of see. I'm just going to sort of sketch the proof of this at a high level. Okay. So towards a contradiction, fix a zero resilient blockchain protocol that's optimistically responsive in the dynamic variable authenticated and synchronous settings. Okay, and suppose the protocol satisfies the definition of optimistic responsiveness with liveness parameter L, which is order delta. So basically, you always have to finalize transactions within time L, which is order delta. Okay, and again, delta denotes the unknown maximum message delay. Okay, so then we can let k be a constant such as L is less than k delta for all delta greater than 1. Okay, and we can choose delta to be larger than k. Uppercase delta to be larger than k. Okay, so we're going to basically what we're going to do here is suppose that actual message delivery is really much quicker than our known bound delta, at least by this factor of k. Okay, and then we consider a sort of standard indistinguishability argument. Okay, so let the player set P be P0 union P1, where P0 and P1, they're non-empty and disjoint sets. Okay, we're going to consider 3 executions of the protocol, E0, E1, and E2. In all 3 executions, the player set is just P. Okay, let's consider the inputs then and the player allocations. By the player allocations, I just mean a determination of which players are active at which time slots. Okay, so it's simple. So the active players are P0 and E0, P1 and E1, and the whole set P and E2. Okay, so P0 and E0, P1 and E1, and the whole set P and E2. Okay, remember we're in the dynamically available setting here, right? So it's we don't have very strong guarantees on when players will be active. In all 3 executions, every player is honest. Don't need any Byzantine action here, and has a unique identifier. Okay, let's look at the resource balances and who owns what stake. So in all 3 instances, we'll just have every resource allocation give every player a resource balance of 1 at every time slot which they're active. Okay, the details here aren't too important. And as far as stake, so we'll consider initial state distribution S0, which allocates all players in P resources balance 1, right, where all the players active. Again, this is not too important because in the dynamically available setting, you can't really, this players having stake doesn't ensure that they're active necessarily. Okay, and then we want to let TR0 and TR1 denote two transactions that are conflicting relative to your initial state distribution. So basically, okay, these are conflicting transactions. Okay, and then, so when a player is going to receive these transactions, that'll depend on the execution. So in execution E0, the environment sends TR0 to all players in P0 at time slot 1. And so a symmetrical thing goes on. So in E1, the environment sends TR1 to all players in P1 at time slot 1. Remember, in E0, it's the players in P0 who are active. The players in P1 aren't active. In E1, it's the players in P1 who are active, and the players in P0 aren't active. Okay, so TR0 is sent to players in P0 at time slot 1 in execution E0. In execution E1, TR1 is sent to all the active players, those in P1 at time slot 1. And in E2, the environment sends TR0 to all players in P0 at time slot 1, right, as it did in execution E0. And sends TR1 to all players in P1 at time slot 1, as it did in execution E2. Okay, and the basic idea is that we want E0 to seem indistinguishable from E2 as far as the players in P0 are concerned, at least for a certain amount of time. We want E1 to appear indistinguishable from E2 as far as the players in P1 are concerned, at least for a certain amount of time. Okay, so how about message delivery? So in E0, remember the players in P0 are the only active ones there. It's very simple. So dissemination at time slot T by a player in P0 is received by the other players in P0 at the next time slot. Okay, and they're the only active players. In E1, it's symmetrical. So dissemination at time slot T by a player in P1 is received by the other players in P1 at time slot T plus 1. Again, it's only the players in P1 who are active here. And then in E2, basically what we do is like a little sort of network partition. It's only of length delta, but because the protocols has to be optimistically responsive, like a partition of length delta is enough. Okay, so in E2, dissemination at time slot T by any player in P0 is received by other players in P0 at time T plus 1, and is received by players in P1 at time T plus delta. Okay. A dissemination symmetrically, so dissemination at time slot T by any player in P1 is received by other players in P1 at T plus 1, and received by players in P0 at time slot T plus delta. Okay. So as I say, the basic idea is here that we're doing a sort of a little network partition of length delta, and that's enough. Basically, the E0 will seem indistinguishable from E2 as far as the players in P0 are concerned, at least for a time of length delta. Similarly, E1 will seem indistinguishable from E2 as far as the players in P1 are concerned, at least for the time of length delta. Okay, so how do we produce a probable consistency violation? Well, then it follows by induction time slots that for each I in 0, 1 and all t less than delta, EI and E2 are indistinguishable for players in PI until the end of time slot t. Okay, so E0 is indistinguishable from E2 as far as the players in P0 are concerned, right? Up until the end of time slot t for all t less than delta. Similarly, E1 is indistinguishable from E2 for players in P1 up until time slot delta. Okay, well, because little delta, our actual bounded message delays here is 1 in the executions E0 and E1, and because delta is greater than k, or uppercase delta is greater than k, the definition of optimistic responsiveness implies that in E0, TR0 will be confirmed for all players in P0 by time slot delta. And similarly, E1, TR1 will be confirmed for all players in P1 by time slot delta. Okay, then we get our contradiction by considering E2. Okay, so from this previous observation dagger, it follows that in E2, similarly, right, TR0 will be confirmed for all players in P0, and TR1 will be confirmed for all players in P1 by time slot delta. Right. And because TR0 and TR1 are conflicting transactions, that provides the required contradiction. Okay, so that finishes the proof sketch. We have a contradiction here. As we said before, though, so in introducing the permissionless setting, we introduced these three new difficulties simultaneously. Right, we have an unknown player set of unknown size. Players can now be active or inactive at each time slot, and we also have the possibility of sybil attacks. And so what we said right from the beginning of the series of videos is that whenever we see an impossibility result, it's going to be interesting to consider which of these three new complexities is really driving the new impossibility result. Are all three of them required, or is one of them suffice to give the new impossibility result? So it's interesting to observe here that the proof we just went through is driven solely by the possibility of inactive players. Right, so the player set P used in the proof can be known and finite, with each player using a unique and known identifier. Okay, so that was a negative result for the dynamically available setting. Now let's see a positive result for the quasi-permissionless setting. Okay, so consider the quasi-permissionless, authenticated, and partially synchronous setting. For every row less than a third, there exists a deterministic and row-resilient proof-of-stake blockchain protocol. Okay, so that, before we even consider the last sentence there, that already gives us one separation between the dynamically available and quasi-permissionless settings. Right? Because the quasi-permissionless protocols can function in partial synchrony. Okay, now that we can prove more than that, so moreover, the protocol can be made a third one accountable. Okay, so that gives us a second separation. So now we know quasi-permissionless protocols can be accountable, and we saw the dynamically available protocols can't be. Okay, and can also be made optimistically responsive. Okay, so that gives us our third separation. Dynamically available protocols can't be optimistically responsive. Quasi-permissionless protocols can be. Okay, so that gives us three different separations between the dynamically available and quasi-permissionless settings. To finish off this mini course, if you like, what we want to do is to consider like one way of separating the quasi-permissionless and permission settings. Okay, so we'll get on with that in the next video.